Hi everyone, I am David Greenberg. We are here with episode 19 of the Machine Learning at Helmholtz-Zentrum Gestacht seminar. We have a really interesting paper today on parameterization schemes for convection and precipitation and moist processes in atmospheric models. It's going to be presented by a new PhD student in our group, Shivani Sharma, who has just joined our group in October. Welcome, Shivani.
Thank you.
And, this paper, before we jump in, I want to give just a brief perspective of why I find this topic so interesting, because it's something we keep coming back to. We really revisited parameterization schemes, and in particular, the schemes related to moist processes, convection and rain, and clouds quite a bit. And I think these are really interesting problems because they bridge different spatial scales, because they have a lot of the kind of the typical challenging computational properties of these aspects where it's difficult but very promising and very rewarding to combine the model-driven and data-driven approaches. And we're having another one of these rainy spells in Hamburg, and anyone who lives here will notice that weather prediction is not so great here. It's not so easy to predict exactly when it's going to rain. This is like this is when you tell people you work in earth science, you say, well, I have this app on my phone, can you make this better? There's a lot of kind of short-term practical applications there. And I think another big one that a lot of people have pointed out is just the role of these processes in climate models and in the climate sensitivity over the long term. Such a small fraction, I think 1 part in 250 of water vapor in the atmosphere is clouds, but it has such a big effect, especially in the tropics, on Earth's energy balance and on radiation balance, which we covered in a few seminars ago. And so being able to deal with these processes in a better way, to tune the models better, to run them at higher resolution, to run them more quickly over bigger areas, would really maybe help us explore the different possibilities to improve these long-term forecasts as well. So they're just really interesting practically and intellectually as well. So the paper we're going to cover today that Shivani is going to present will mainly focus on neural networks, but also compare to some previous results by the same group using random forests. And random forests is a different machine learning technique, which we haven't really covered so far. I'm going to give a brief, very simple introduction over a few slides of what random forests are, and then I will turn over to Shivani to present the main paper, which is going to be, I think, a lot more interesting. So random forests, I'm going to cover three kind of aspects. I'm going to just explain the idea of using decision trees for classification, a whole different approach compared to the neural networks we've considered so far, but also a kind of machine learning, in that it's a kind of function learning that can be iteratively improved with new data. Then I will talk about how random forests arise from these decision trees plus a few extra twists. Then I will explain how to do trees for regression instead of classification. And I'll sum up some advantages and disadvantages. I'll move pretty quickly. I'll be very superficial. And there's a lot of good resources if you want to read up on this further. So, okay, here's a simple problem where we might use a decision tree. We see some mushrooms in the woods. This happened to me recently. I did not try to eat them on a walk this past weekend. You can see mushrooms growing in the woods in Hamburg. And as a disclaimer, please don't try this at home. You have different kinds, and you want to know, is each kind edible or poisonous? So you could have a kind of a flowchart diagram. You could say, is it big or small? If it's big, we want to know if it's yellow. If it's not big, is it spotted or not? And if it's spotted, is it big spots or small spots? So we have a kind of a flowchart that we can follow. And the idea of these decision trees is to automatically build these tree flowcharts based on data sets. So we have some input variables like, okay, is the mushroom yellow? Is it spotted? Is it large? Are the spots big or small? And then we have output variables, poisonous or edible. And then based on a training data set, we're able to build the best tree to fit that data, to predict the output, poisonous or edible, from all these inputs. Okay, So how do we do this in practice? Here's a simple data set I've taken from this data science blog. Say we're looking at petals of a flower, and the petals have a length and a width, these two input dimensions. And then we want to identify the species of the petal. It could be setosa, versicolor, or virginica. Okay, there's three different, and we're marking these as the three colors. So here's the data as a scatter plot. Given a point in this space of petal length and petal width, we want to classify the point as belonging to one of these three species, one of these three colors, one of these three categories. So we're trying to learn a function, just as we would with a neural network, where the inputs are these two variables, length and width, and the output is a label of one of three categories. Okay, so how do we do this? We start with all the data, and what we do is we try to find the best possible cut. So we look on both axes, we sort the data, we look at all the possible cuts between the data points, and we say which one gives the best segregation of classes, and the exact measures, the mathematical formulas you can find in these papers on decision trees. But basically what we'd like is to have, on either side of the cut, we'd like to have as much as possible all the points only falling into one class. So it turns out that using a standard one called the Gini impurity standard measure, we want to cut here. So basically we end up cutting on the petal length dimension, and we say if the length is less than, greater than, or I'm sorry, less than 2.45, this is wrong, we're going to classify it as a setosa, otherwise it'll be verticolor. Now why are we just assigning one color to this group? Because we just have one output for each branch of the tree. So it's either setosa on the left or versicolor on the right. So this is not so good with only one decision. So then we can keep going, and we can consider further cuts. We can cut again on the same axis in a different place, or we can cut on a different axis. And so we do this several times, each time taking the best cut. And after 3 steps, this is what we get, right? First, we've cut it, I think, on the length axis, and then we've cut it again on the length axis, and then we've cut it on the width axis. So we get all these rectangles, and we color each rectangle a different color. So this is the kind of function that these trees can learn. We're coloring rectangles of the input space according to the majority label for the data inside them. And then, of course, having learned this function, having learned this tree, we can apply it to new data points which weren't in our training data set. So these are decision trees. There's subtleties about how you train them. You can limit the depth of the tree. You can use different strategies to explore things, and we'll cover a few twists in a second. But this is the basic idea of decision trees, and if something isn't clear, just anyone can chime in on the chat or say something on the Zoom call. We'll be keeping an eye on the YouTube chat as well. Okay, this is decision trees. What are random forests? As you might guess from the name, a random forest consists of a bunch of these trees. But why random? Okay, so we're going to add a couple twists to the process of fitting these decision trees. The first twist is at each step when we make a cut, we don't make the best cut of every possible feature. We choose a random subset of the features and choose the best cut of those. And this isn't such a big deal in the 1- and 2-dimensional examples I might have showed you, but when you get to hundreds and thousands of input features, it makes a big difference. So you just take a small number or a moderate number of these input features, and you choose the best cut to separate the categories along one of those axes. So the tree will be random in which sets of variables were chosen at each step. That's twist 1. Twist 2 is we're then going to repeat the entire process of building the tree with different random subsets. So maybe we'll choose 80% of the original input-output data and fit a different tree with a different 80%. So we keep choosing a different 80% of that input of the data set, fitting a tree to that. So these trees are doubly random. Random because they're fit on random data, and random because they choose a different set of features to use at each time we split one branch into 2 branches. Now we keep going till we reach a maximum depth we've chosen, or until all the labels on each branch are the same in our data. And so having built a bunch of these trees, we can combine them. We basically average their predictions to get a probability for each class label for a point. So given a data point, jumping back here, imagine if we had a lot of these trees. So here's one tree, but imagine if we had a lot of them. If we chose a new data point, we'd calculate the color for all of these, maybe tens or hundreds or even thousands of trees, and then let the trees essentially vote on which label to assign that point. So these are random forests. Now, up till now we've been assigning labels. What if we want to output values that can value continuously? We basically go through the same process of making cuts to get the best performance. Now we're trying to minimize mean square error of our predictions of the values. But then in each of these rectangles, whereas before we would choose the majority label, now we take the average value. So here it is in one dimension. You can see if we go to a tree length of 2, then we have a tree depth of 2, we have 2 to the second is 4 different, well, these rectangles are now just line segments on the x-axis, and we can take the average value on each of these 4 blue segments. If we go to a deeper tree, we have 2 to the 5th, or 32 different segments of the x-axis, and for each one, the tree will output the random variable, the mean of the data. And so then we fit this function, just like a neural network would fit a function to our data, and we can then use this on additional data. Here it is in 2 dimensions. Again, we have rectangles, but instead of coloring the whole rectangle based on the majority class in our training data, we're just going to take the average output for that rectangle. And again, we do these cuts in order to keep the, basically to minimize the variance of the values compared to this mean. Okay, in each rectangle. So this is decision trees for regression, and we build a random forest in the same way. We choose random subsets of the data, we choose random variables at each cut, and we build a forest. And then we let them vote, but now instead of voting by majority, we take an average of the outputs of the different trees. So these are random forests. And compared to the neural networks that we've used, they're very, very different objects, but it's still machine learning. So what are the advantages? They're very flexible. There aren't many parameters to tune. You don't really have to choose that much about how you build your trees. You can choose a few things like the maximum depth, but it's nothing compared to the wild zoo of different neural network features, different kinds of layers, different kinds of convolutions and recurrence and attention, and different input-output functions for your units, different kinds of regularization, learning rates. We just don't have any of that. It's much simpler to use. There's very good standard implementations like scikit-learn is used by almost all the papers, and you can really get it going in minutes on your data. At least for small trees, these flowcharts are interpretable. You can kind of understand how the algorithm is making decisions. Although I think when you get to very deep trees, even if you could understand each step, it's very difficult to understand the whole process. And they train quickly. And why might you not want to use them? If you look at standard data science, machine learning benchmarks, you do see better performances with neural networks on most tasks. They require more computation to train. They may require more specialized hardware like GPUs to train effectively, but they do better than random forests on most tasks, especially the regression tasks. And it's kind of easy to see why, right? That if the function I'm trying to learn is smooth, as I can see with this kind of sinusoidal-like wave, you'd have to use a very deep tree with very, very many levels to fit it smoothly, whereas a neural network can learn smooth functions with relatively few layers and units. So fine details are maybe a problem for these. There's a memory cost which can arise, and if you search for random forests, you'll find a lot of people complaining on Stack Overflow or GitHub about, hey, my algorithm ran out of memory, and it's a big thing. It's just because you have to keep all these trees in memory. They're not differentiable, right? So if you have a tree which is going to map inputs to outputs, which are either class labels or values, you can't differentiate through it, which means certain tasks like uncertainty quantification or sensitivity analysis, which you can do easily with neural networks, are not so easy to do here. And it's not easy to combine them with other techniques like neural networks in a kind of a combined optimization procedure. You can't differentiate through them. There's also fewer Lego blocks to build with, right? Like in the sense of how you build the networks. This is an advantage and a disadvantage. But if I know that my data has spatial structure, I can use convolutional nets. If I know it has temporal structure, I can use recurrent nets. If I'm using random forests, there aren't really commonly used components I can use to exploit that structure. And finally, they're less optimized for modern GPUs, right? Modern GPUs work well when all the the data access patterns are kind of the same in parallel, but because trees fundamentally have branch points and run different code depending on the data, they just don't exploit GPU hardware as well. But okay, that's my kind of whirlwind introduction to random forests. With that in mind, I'm going to turn over to Shivani to get into this really interesting paper.
All right.
I see we already have a question, but let's wait a little bit for past the introduction, and then we'll get to it.
All right. Today's paper basically tries to tackle the problem of using machine learning parameterizations in atmospheric models instead of the physics-based parameterizations that are traditionally used. So the reason why there has been a lot of research related to this recently and a lot of papers, one of which was already covered in episode 10, is because traditional parameterizations really simplify the physics that goes into the models. And because of that, the models can generate outputs which can be very inaccurate at times and can lead to large biases. And if we want an accurate output from a model, usually you would expect that as you go more fine on the resolution, the results would improve. But it's not always possible to do that. So it really leaves no other option but to run a coarse grid model and then use some kind of parameterization. So this is the idea behind using machine learning parameterizations. Maybe that they may be able to represent some of the subgrid atmospheric processes better than the traditional parameterizations, and can then be used within atmospheric models for improved results and also for speeding up the model. That's another thing. In this paper, they build on some previous work that has already been done in this field. And right now, I'm going to go through some of those points and discuss one of the biggest problems that comes to using these parameterizations. So one of the most common issues when using machine learning parameterizations is that they do tend to perform well when you are just training and testing the data without plugging it into the GCM. But as soon as you couple the neural network with the GCM, the model can blow up. And this can lead to a lot of phenomena being observed within the model which might not be realistic, such as grid scale storms that this paper had. And another problem that is commonly observed is a climate drift. And in this paper by Bernowitz and Bretherton, they observed that the climate drift becomes apparent just after 10 days of running the model. Another problem was some of the outputs that you would generally not expect to be negative when coupled with the neural network can actually turn out to be negative, and this is a problem that has been reported in all three of these papers, which makes the output of the model pretty unrealistic if you think about it. And another problem is that these models, this quantity, column integrated moist static energy, this is a quantity which is again mentioned in the paper. We'll discuss about it later in the detail, is not conserved. So a quantity like energy not being conserved implies that we are dealing with something that is not physically plausible in a way. And this paper tries to address some of these problems. And
sorry, Shivani, are we supposed to see your full screen presentation right now?
Yes.
Okay, we just don't see the first slide.
I think you're sharing the wrong monitor, perhaps, or the wrong window.
You're seeing this, the first slide.
We're seeing the.
Yes, we see.
Mm-hmm.
We see your browser, kind of.
Mm.
Yeah, your Google Docs.
Really?
And the first slide, yeah.
Because I'm I just shared the whole of it.
So maybe if you adjust your zoom settings, you can share the other screen or the other window.
It's actually the same window. I just clicked on present. It should go to full screen. That's all.
Is it possible you're sharing a specific window instead of your whole screen?
Let me do it again.
It wouldn't be a normal machine learning seminar without at least one technical problem. So you're in good company right now. There we go, great.
So these were the points that I was referring to. Maybe I should go through them again quickly. So the first problem was related to stability, that neural networks are not that stable when they're actually coupled with an atmospheric model, and this can lead to the model presenting some unrealistic phenomena. The other one, which is quite common, is a climate drift that is observed within a few time steps. In this particular case, this particular paper, it was 10 days. The other one is certain variables which shouldn't actually be negative, such as precipitation, coming out to be negative. And this is a common problem that has been observed in all three of these papers. And another one is the, as I mentioned, about related to conservation of energy. So whenever the neural network parameterizations are plugged into the atmospheric models, the energy, the quantities related to energy and moisture that should be conserved are usually not conserved, which means that something physically implausible is going on. So in this paper, they try to address these issues and come up with their own interesting ways of dealing with these problems. So first, we're going to look at how they generate the data for this task. They use a very simple aquaplanet model, and the resolution. So there are three different models involved here. One is the high resolution model, which runs at 12 kilometer grid. X8 and X16 are 8 times of 12 and 16 times of 12, and X8 NNN and X16 NN are when machine learning parameterizations are plugged into the coarse resolution model. So how are they actually calculating the fluxes that are involved in this process? So this is the quantity on which the neural network is trained. These are the subgrid fluxes. And how do they go about calculating the subgrid fluxes? So this here is resolved. So the overbar represents the output from a coarser model. And this is considered a resolved flux. So resolved flux is when output from a high resolution simulation is coarse grained, depending on which model you are considering, X8 or X16, coarse grained according to that particular model, and then it is plugged into the coarse resolution simulation, and the output from that simulation is called the resolved flux. It is called the resolved flux because ideally it is supposed to capture the things that are happening at a higher resolution and be able to represent them within the lower resolution. And from this, we subtract the other term, which is the flux at coarse resolution. So the flux at coarse resolution is simply calculated by using the output from the coarse resolution models. So the idea here is that whatever is not resolved at the coarse resolution would then contribute to subgrid scale processes. And yes, so and this is how the subgrid fluxes are calculated. And these fluxes are then what the neural network is trained on. And then the trained neural network is what is used in the coarser model. Instead of using the high resolution simulation, we use the trained neural network. And the idea is that once you Okay.
So thank you very much for that.
Okay, it looks like the YouTube stream is back up. I'm going to write everyone there. All right, so Shivani, if you please continue.
And yeah, so I explained the third point. And the last point was related to, so in the papers that this work has cited previously, and I also discussed them briefly in the second slide, precipitation is usually an output of a particular neural network. But here they have not done that. They are diagnosing precipitation and calculating it through the output of other variables, which are the output of the neural network. So all these things are done with the intention of ensuring that this would make the machine learning parameterization would add more constraints to the machine learning parameterization. And we'll see how they manifest themselves one by one. So the first thing that, this is just an explanation of how the difference between how tendencies and subgrid fluxes would work. So this can be considered a column that has been divided into vertical levels, 4 vertical levels in this case. And this could be any quantity, for example, some changes in energy. Otherwise, if these two were also the output of the neural network, it can totally happen that then this equation might not hold true. The numbers would be very close, possibly, but this kind of puts a physical constraint on the value for these two numbers in relation to the value that they have with Qt. And this is what the second point was about, choosing which variables to be used as the output for the neural network, and which that can be diagnosed directly to ensure that moisture and energy remain conserved. The second part of the neural network outputs diffusion and surface fluxes. And the input here, they have more inputs here: SST, surface wind, other wind vectors, Qt, and temperature. And this is also important that they have actually predicted diffusion, which was something that was not always done in the previous papers. And they have actually predicted diffusivity, not diffusive fluxes. So this ensures a diffusivity value can be used both for energy-related fluxes and for moisture-related fluxes, which would ensure that both of them kind of, the changes in one are represented in the other one as well. Right. This is the picture from the paper itself, where they have shown all the fluxes and the two neural networks. Now on to the results. So they haven't really compared the direct outputs from the neural network, but instead the online performance of the neural network, which is that when the trained neural network is plugged into a GCM and the values that you get out of it. So in this, they have considered the high resolution output, which is the output that you obtain from the 12-kilometer grid spacing model, as the benchmark. It is represented in blue over here, and as you can see that while the X8, which is the coarse resolution simulation, does not really match the high resolution simulation, once you plug in the neural network into the coarse resolution simulation, the orange one, it follows it pretty close. And same is the case for X16 as well. And when you look at precipitation distribution, you can see that maybe X8NN has more tendency for extreme events, but it follows more closely the high resolution simulation than the X8. It's the same with X16 as well. And this was something that I noticed in the paper, that they have use a particular equation. It's written in the supplement for calculating precipitation, which does not quite seem to be correct, actually. So I have picked up the equation from their previous paper where they use random forest to solve this exact same problem. And this is another one of the clever tricks that they have used, which is not predicting precipitation directly. So the most major part of their work related to random forests was done in the previous paper, and in this one they are mostly focused on the neural networks, but they do compare the results from their previous paper on random forests and on neural networks. So this is again how things happen online, which is when the model is run. And there isn't as much difference in the performance of the model with random forest and with neural network. The random forest and neural network, both of them actually do pretty well in following the high resolution simulation in both these cases. But the interesting thing is when you look at the offline performance of them. So offline performance is when you're just comparing the output from the machine learning parameterization without plugging it into the model. So these are some three of the values that they have looked at: QT, HL, diffusivity, and here we can see almost in every case. So on the x-axis it is the R² value, that neural network and random forest have different, they do not perform the same actually. The neural network in most cases gives a higher R² value than the random forest. Same is the case over here. And same is the case with diffusivity. You get a higher correlation values in almost all these cases. So this is quite interesting in the way that just because one particular model performs well in an offline mode does not mean that it's going to translate to good performance once that model is plugged into a GCM as well. As we saw that in this case, there is some noticeable difference in the way the neural network and the random forest parameterizations perform. The difference isn't large enough when you look at the online performance. And lastly, they have also discussed neural networks at reduced precision. So one of the reasons that reasons that they give for using neural networks over random forests is that neural networks can be worked with at a reduced precision as well. So these figures are from the supplement, and in the supplement they have actually calculated the R² values. And in that you would find that even at reduced precision, the output from the model of course, if you go to 1 bit, it does not perform as well. But for example, dropping it down to 7 bits does not change the performance as much as one would expect. That being one of the advantages of using neural networks, that they can be used at reduced precision.
So this was a discussion we were having a little bit before. If anyone can explain to us how 1-bit arithmetic works in neural networks, I'd be very curious. I can imagine how 8-bit works, but even 7-bit, but 1-bit is quite interesting.
Okay, and the last thing that they have discussed, again in the supplement material, is that they have worked with the different number of layers for their neural network. They ultimately picked the 5-layer neural network, which was their default. But they have also done experiments with 2, 3, and 4 layers. And while, of course, if you use a very shallow network, for example, a 2-layer network, it does not at all match the intended results. Same is the case over here. But if you drop it down to, for example, 4 or 3 layers, the model does not perform that bad. And that is also one of the things that I think they have mentioned in the conclusion, that the scheme that they have created by using all these clever tricks, I would say, is such that it's very robust. That even if you change a few things in the model, it can still give very good results when it is coupled online with the model. So yeah, these are all the results and the structure of the model and all the interesting things that they have done in the paper.
Thanks a lot. That was a really great explanation of some rather complicated research. I knew we wouldn't capture every technical detail of this. There's a lot going on, but I think we covered quite a lot. I know I have questions about this. Let me get to the first one from the Zoom chat from Felix Stieler at ITCZ. Felix is asking, on page 2, the authors state the following. Random forests might be more stable than neural networks since their predictions for any given input are averages over samples in the training data set, and thus they can automatically satisfy physical constraints such as energy conservation. Is there a good explanation for this claim? I'm not sure. Do you know the answer to this, Shivani? I can give a partial answer, maybe.
I can only imagine that if, for example, the input values are way outside of the training data, then I would imagine a random forest would still give more sensible results than a neural network.
Yeah, that makes a lot of sense, right? Because the mathematical functions defined by the neural network they're trained to give the right result on the training data, but they could go to very large or very small or negative values if you go outside the training data. Whereas random forests will give you basically the output will always be an average over a subset of the training data points outputs. The automatic satisfaction of physical constraints is a little more puzzling, considering that in that other paper, YOG20, I looked at it briefly, and I know they do discuss this issue in an appendix. So this could be a good place to start. This is in Nature Communications. I could imagine that maybe if some of these conservation laws can be expressed in terms of linear relationships of inputs and outputs, maybe by always defining things as averages, they tend to be satisfied. But I'm really not sure. I think this would be worth a look. So I expected maybe more questions because there was a lot we covered in this paper. It was really, it was just full of clever ideas, and I mean, for me, one of the key messages here was they didn't try to do too much, right? Like looking at other parameterizations, like the neural network trait on the superparameterization in RASP PNAS paper from 2018. They do radiation and precipitation and convection and temperature effects. They even talk about doing momentum transfer. It's so much for the neural network to do. Here they use multiple networks and they give each one a very specific task. And so they very carefully design the tasks for their machine learning algorithms based on understanding of the model. Another question from the chat, Hagaman asks, can you explain how the fluxes are used instead of tendencies when giving back to the climate model? So I think, Shivani, you covered this sort of in some of the earlier slides. Maybe we want to jump back to those and yeah. If you imagine these are values are something like moist static energy or mixing ratio of cloud ice or something at each z level. And then the neural network can output a tendency, right? Which is the rate of change of each of these at a different z level. But there's nothing preventing this from changing the overall amount of the quantity when it should be conserved. Whereas if the neural network outputs fluxes, and then instead of directly using this to update the state of the model, I think this was the next slide, you use this and compute tendencies based on those fluxes. Those flux derived tendencies, those flux derived rates of change, will always maintain the conservation of your quantity, be it energy or matter or what have you, because you're not creating or destroying anything. The neural network is telling you how much to move things around. And then you can see the outputs that Shivani has put on the boundaries between the cells. And they do this in this paper as well, right? The outputs might be fluxes in between different Z levels instead of rates of change at different Z levels. Does that answer your question? Hope so. We have another question, I think an interesting one from the Zoom chat about the difference between RFs and maybe neural networks, or about RFs, or random forests. Eduardo Zarito from HZG asks, random forests cannot extrapolate beyond the range of the training data. Is this right? I mean, technically, I think that's right. It seems that their outputs can never go beyond the range of the training data's outputs. But of course, so neural networks can do this successfully, and do this successfully in some cases. But in fact, both methods are going to have difficulties when you use them on data that doesn't resemble the training data. This is just a limitation of machine learning in general, that it's not going to create knowledge that wasn't presented in the data. You can fill the gaps using careful knowledge of physical laws and incorporating them in the training procedure. You can do very clever things like doing fluxes instead of tendencies and similar tricks. Yeah, this is a limitation. And then there's disadvantages and advantages of both, right? With a neural network, your output could go way up to infinity, but it can also go outside of the training data's outputs. With random forests, you're stuck with what the training data gives you, but you also won't blow up and go to infinity. So is still asking, so can we go back to this slides about the advection and fluxes? I don't get how the final condition is determined in the figure from the initial condition and advection. Great, so let's go one forward. Right, so here we have let's say we're talking about more static energy in 4 Z levels, right? And then this would be, I guess, whatever joules per kilogram or whatever units you're using here. But we have 1, 2, 3, 4, right? The advection says we're going to have a flow downward between the first and second cells, no flow between the second and third cells, and a flow of 2 between the third and fourth cells. So the first thing we do is, based on the first flow of -1, we take one kind of unit of Moivre static energy from the second cell here, which I guess you're going to see on the YouTube stream with my mouse, but not the Zoom call. We're going to flow from the second cell to the first, right? Which is why in the bottom final condition, we've moved 1 unit from the second cell and assigned it to the first cell. We haven't moved anything between the second and third cells, and then we have a positive flux between the third and fourth cells, which is why we've taken this, which has 3, reduced it to 1, and those 2 units have moved into the fourth cell. So at each boundary between cells, we say how much flow is going to the left with a negative value, or to the right with a positive value. So I have a general question about the networks that were used in this paper. We know that they have 2 to 5 layers, but what are these layers? How many units do they have? And what are they, fully connected layers, or what's going on?
Yeah, they are fully connected layers. They haven't done anything other than using fully connected layers. And I think they mentioned 128 nodes or something.
128 units, okay. All right, so these aren't so small, they aren't so big. I think, Shivani, you mentioned when we were talking about this paper that they actually fit these on the CPU. They don't even need GPUs to fit them because they're fairly small.
Yes.
I mean, I think this gets back to what I think is one of the disadvantages of random forests. Unfortunately, they haven't made. This is a good question.
I mean, their idea behind it was they wanted an output which would as closely as possible match the high resolution output. And once they got near to that, I think they, I mean, they haven't mentioned that they went any deeper than that. So I'm assuming they started with two layers and moved up. And then they got a good correlation value between this and the output from the high resolution. I guess, yeah, they pretty much stopped there. Looks like it.
I mean, if you keep adding layers and between 3 and 4 and 4 and 5 nothing happened, at some point you can stop.
Yeah, there's not a lot of difference when you go from 3,
Yeah.
4 to 5.
But something could happen at 10 layers or something.
Yeah.
I think there's also a good reason not to go too deep here, which is in the end, the idea is to embed this in a GCM and then run it for decadal simulations, right? And there it's nice to have a very small compact network which is fast to compute. This is a question that came up in some previous seminars. Is they didn't really mention this much, but I don't think in either of their papers, I'm not sure. But, well, how do you actually get this thing back inside the climate model? You can generate data pretty easily. You can dump it out of one of these simulators. But then to actually take the trained network and couple it to the simulator may require writing Fortran code or having Fortran and PyTorch or TensorFlow communicate with each other. And I don't really know how they did that. Did they say anything about this?
I think that at some point they mentioned that they saved the neural network and loaded it into Fortran, which I'm guessing is saving the weights and biases.
Yeah, I mean, this is certainly a viable option. At some point, it would be, if these things become very common, I think people will want to use GPUs to run the neural network part of their models, which will mean they won't be writing pure Fortran code. But how to do this effectively is sort of a big open question. Yeah. Zeguo from, I hope I'm pronouncing this right, from Zoom chat asks, does this work belong to a function mapping problem? So are we, I would understand functions, so are we learning functions? If I'm understanding that correctly, we are absolutely learning functions. And these functions map inputs, which are basically things like the fractions of different types of water in different sea levels. I think we get up to some 6 types of water in this model. Stuff that's falling, stuff that's in a cloud, ice, snow, water vapor, and then you have overall moisture. So you have all these variables, you have moist static energy, temperature, and then based on this stuff, not all the variables, but some of them, we're going to have a function mapping that to outputs, which are fluxes and diffusivities, and in some cases, tendencies as well. So we are learning functions, yes. Basically, anytime you're doing machine learning, there's usually... Okay. Any other questions from Zoom chat or from the YouTube channel? If not, let me thank Shivani again for an excellent presentation of a really nice paper. There's a lot of cool ideas in here, which, especially this learning fluxes and learning diffusivities, which I think can apply to a lot of different scenarios, not only parameterization learning, also maybe when you want to learn the whole model, like in the last seminar, or even other applications like just database forecasting and super resolution. If you learn how your data are supposed to move around instead of how they should go up and down in one place, this may be a very powerful strategy. I think we will do one more seminar before the end of the year before taking a break. We had really persistent problems. I didn't want to keep interrupting, but with the YouTube stream this time, so I kept restarting it. I think in the future we're going to record the whole session as well as streaming it live so that we can fill in any missing gaps on YouTube. As always, if you want to suggest a paper, please do let us know. If you want to present your own work for 5 minutes, please do let us know. Thanks again to everyone for participating.